Hello and welcome. Hopefully you've had a chance to watch the Bad Apple demo as ported to my Homebrew pipeline CPU. If not, you should probably go and watch that now. Whenever I release a new demo like this, I always end up with lots of questions about what the challenges were and how I overcame them. So this video is designed to give a few answers to those. Let's get into it. This video is about the process of developing and porting the video to this system. It's not about the video itself. But I will start off with a small talk about the Bad Apple video because I think it's important to recognize where it came from. Then I'll talk about the graphics rendering. Now the VGA system I've built for Jam 1 has got a tile-based rendering environment, which makes this quite difficult. So there were some challenges there I think people would be quite interested in. Then I want to talk about timing and streaming the data. The compression of the graphics is quite an important part. And finally, the sound is of course quite a significant part of this demo as well. The first form of the tune was made by a game developer called Zun, who used it in his fourth Tahoe game that was released in 1998. He was developing those games for a 16-bit NEC PC. In 2007, a remix of the tune was created by the Dojin Circle. This was all able to happen because Zun has a very open policy on his music and IP, and there's really quite an interesting community is built up around his works. Then in 2008, a storyboard was released by a fan who called themselves Moo. It was very crude, but it contained an awful lot of the interesting elements that we now know in the final video. And that storyboard came with a request for somebody to animate it, and a user by the name of Anira took up the challenge and produced a video that is now quite well known. Now, from the mid-2010s onwards, demo coders started to release versions of this video ported to various computing devices, and it kind of became a thing, and of course that's what's brought us here today. I took up the challenge to port it to my homemade system. Some of the information here I first learned from a video called Bad Apple Explained, and I recommend you go and watch that if you're interested more in the background of the original source material. I'll also provide a link to a playlist that has a large number of different Bad Apple ports to different systems, which is quite a fun watch. If the display circuit was a standard full-screen bitmap buffer, this would be simple. I'll just scale and compress the color depth of the video until it fitted within the capabilities of the system, and we'd just be drawing that to the screen. But that's not what I have. The display hardware works more like an early console or game system. The display is 640 by 480 pixels, but I control that by means of an 80 by 60 tile map where each entry selects one of 256 tiles, which are in turn 8 by 8 pixels apiece. So in many regards this is quite like a text mode, but I have 4 bits per pixel in each of the pixels of those tiles. Now the beautiful shadow play work in this video is not going to smoothly fit into this system, so that was a technical challenge that I had to work around. For my experimentation with the graphics, I did pay particular attention to some specific scenes which I knew had a variety of different things I was going to need to solve. Remu at the start is quintessential, the transitions are very important to get right, and these fire effects are going to be quite different than the sharper contrast graphics. And the Prism River sisters at the end are quite detailed and dynamic. So to do this, I need to choose some tiles. The first thing I did was to put a simple 256 grayscale ramp into the tile data, and then that makes the tile map a very primitive 80 by 60 grayscale graphics mode. So it'd have low resolution but great range. You can see everything kind of worked, but that resolution is really quite coarse. I can only really access 16 entries in the palette from the tile data at the moment, so the next thing I thought of doing was creating a set of tiles that would encode all the permutations of a 1x2 coarse pixel grid. So this essentially gave me an 80 by 120 16 grey level graphics mode. That's a definite improvement on what we had before, but you can notice the pixels are twice as wide as they are high. So then I moved on with that process of trading grey levels for more resolution and switched to 2 bits per virtual pixel. So I created a tile set that encoded all the permutations of 4 pixels at 4 different grey levels. And that means we can have an effective display resolution of 160 by 120 with 4 grey levels. Okay, so the outline is sharper. We could definitely feeling the drop in the grey levels. But overall, I'm still not quite happy with it. I'd like to get the outline sharper. So the next thing I tried is something I'm calling a rotating boundary set. Now take the 8x8 pixels of the tile and imagine drawing a sharp boundary on that between the light and the dark. And then imagine rotating that boundary and creating a series of tiles at different angles. And then for each of those angles, imagine pushing it forwards or backwards along the axis perpendicular to the line. And that's what I did to create a set of tiles. So this test set had 32 different angles and then 8 steps of displacement, giving a combined total of 256 tiles. Now the contrast is much superior, but all those areas like the fire, which showed gradations of intensity, are not working very well at all, or the shadows. But this technique did give me hope that I could come up with a solution that was going to look nice and high resolution. So I decided to try out a hybrid approach. So I started off with a tile set containing 16 grey levels as solid blocks. Now this would be very low resolution, but it would let me draw more interesting gradients like you see in the fire. So I added to that a rotation set with 29 angles and 7 displacements. This doesn't quite have the fidelity of the 256 entry set, but it does work almost as well. And then I used 81 tiles to create a 2x2 pixel tile set with 3 grey levels. Now I didn't expect any of these to be quite as good as the original standalone test, but each has different strengths and weaknesses, and the hope was that combined they'd produce a better final rendering of the animation. Only one problem though, that's 300 tiles. Now, it was very easy in the first step to remove 37 tiles because they weren't used when I ran them through my processing code. Now, this is either because they just weren't needed, or in many cases they're duplicates. Tiles with a solid grey level are already included in the initial 16 grey level tiles, and in the rotation set some combinations of rotation and displacement produce entirely black or white tiles, or ones very close to it. People quick on the maths will know that's still over the top, but what I did was I ran it through my conversion code and sorted each of the tiles into the order they were most commonly used. And so I simply removed the 7 least frequently used to get my final 256 tiles. It's not perfect, but the overall reproduction I think is excellent. I was very happy with that. And that left me able to move on to other challenges in the demo. Let's move on to timing and streaming. I'm going to start this with a look at the VGA signal. So we've looked at this quite a lot in the VGA series, but the VGA signal is 60 Hz and each frame is divided into the visible section and the non-visible sections. We have the horizontal blanking interval and the vertical blanking interval, and we want to limit our updating of the main display buffers to those blanking intervals in order to avoid any corruption on screen, because the VGA circuit only has enough memory bandwidth to support either read or write in a single cycle. Of course, the CPU isn't dealing in the pixel clock rate, it deals in its own clock rate of 4 MHz. So we can divide that by the pixel clock and find out how much time we have in CPU cycles for each of those intervals. So we've got 25 cycles in the horizontal blanking interval, that's not a lot of time, and in the vertical blanking interval we have 5,714 cycles. So what can we do with that? So we're going to work out how that timing is going to relate to our animation. Now I've redrawn the way the visible region relates to the blanking intervals, and I'm going to base my update on each of the VGA frames. So the first thing I'm going to do is update the sound. The second is the video image. Then I can update the lyrics, and that leaves the remaining of the visible section of each frame in which to do my streaming and any other housekeeping I've got to do. Now some people will wonder why I've put the sound at the start, particularly since that vertical blanking interval is quite valuable, but it doesn't take very long and I've got a good reason for that I'll discuss later. So let's talk about the format of the data. The copy of the source video I've got is 30 frames per second, and the length of that is 6,569 frames. But the VGA is 60 frames per second, and we can deal with that by outputting each of the source video frames twice. So from here on out, when I'm talking about frames, I'm talking about 60 frames per second. But we may drop frames if it takes us more than the allocated amount of time to read from the SD card. Part of the SD card specification is for a read we have to wait up to a potential 100 milliseconds for the read to be acknowledged, which is far longer than we can afford, but the vast majority of reads happen in far less time. So let's talk about the data we've got. So the audio data came in at 88 kilobytes, a maximum of 9 bytes for each frame, and an average of 6.7 bytes per frame. The animation data came in at just under 4 megabytes. I'll talk about the compression later, with a maximum of 680 bytes in each frame and the frame average of 359 bytes. Unsurprisingly, the lyrics came in smaller than anything else. We have an average of 1.2 bytes in a frame, and that's far higher than you might expect because it takes me a minimum of 1 byte just to say there's no lyrics data, so the vast majority of frames just have a byte signifying that. Now, if we color code those types of data and talk about how we store them in the file, rather than putting them one after the other or in 3 separate files, I cut up single frames worth of data and interleaved them. So the 3 different types of data for each 1/60th of a second frame are all held together. And that makes it a lot easier to stream the data in and keep everything aligned in time with one another. The main synchronization work is done generating that stream of data rather than anything we particularly have to worry about at runtime. Now, in the demo, I do use the UART to output the lyrics, so let's briefly talk about that. And the first thing to say is there are English lyrics. I didn't know this when I started the process, but when I went looking for copies of the video to start my processing on and evaluate, I found this archive.org page which contained a whole set of resources, and that included both Japanese and English lyrics. That link will be in the description so you don't have to type it in. Now I'm outputting the lyrics over the serial port to the console, so I needed to limit myself to 9 bytes per frame. And the reason for that is the UART circuitry. It runs at 115/200 baud, which is roughly 10 kilobytes a second, roughly 1 millisecond per byte. And we have a parallel interface to the UART, so we can output data to it extremely fast. The first 9 bytes we can output in just 23 cycles. The first byte is immediately pulled into the output shift register, and the following 8 bytes will go into the transmit FIFO. But once that buffer is filled up, we have to wait for individual bytes to send. So that's going to take us something like 400 cycles for each byte. So it wouldn't take very many bytes to start imposing a serious change to our 1/60th of a second. But that doesn't matter too much because there's not that much data in total, and I could make the slowness a bit of a feature. So the subtitle file had time intervals for each line, and then outputting that, I would pause after outputting 9 bytes of data, but every time I got to a space, I'd just wait a few frames, which made the output of the lyric subtitle just a little bit more interesting. If you watch very closely on the video, you can see this action play out on the transmit FIFO's capacity LEDs. Let's talk about the compression. So with fixed tile data, the visible portion of the tile map is 4,800 bytes. That's too much to stream in, and it's too much to update to the screen in the blanking interval. So we're going to need to compress the data. There are 2 main types of compression that come into play on this. We have delta compression. So what we do here is we look at the data after we've converted the base animation into our tile map representation, and we look at each tile and we look to see if it's changed from the previous frame. So Here we can see our test section of video with red showing all of the tiles that haven't changed and then the tile data for the bits that have. We can also look at run length compression, and that's where sequences of values in the tile map are represented by the same value. And that's the green bits in this annotated form of the video. And in the case of this particular video, that tends to mostly be sections of solid white or solid black. The blue sections are more complex data where we're just going to need to store what the individual tile values are. And now we need to think about how we're going to store it. And it's important for us to strike a balance between decompression speed and the ratio of the compressed data. There is literally no benefit to us of a better compression ratio if it fits on the disk and inside our streaming performance budget. So how are we going to encode it? My first thought was to do similar things that I've done before in this kind of situation. We've got 3 operations. We've got a skip, a run of constant value, or some raw data we're just going to copy into the output buffer. Now this is a nice bit-packed form of this. So we've got a skip of up to 128 bytes, or a run of up to 64 bytes, or a copy of up to 64 bytes. This would produce a fairly compact representation, but separating out the codes in the top bits from the count will take a few logical operations. So once I started to create an optimized code plan, the implementation started to look quite different. Instead of packing the type of operation and the lengths into a single byte, I separated those out into 2 separate bytes, which makes the decode a lot simpler. I also removed the skip operation. Now the reason for this is very simple. Taking a value and adding it to a pointer is a several cycle operation. And I realized that if I expanded the skip size out to 16 bits, I could guarantee that every skip operation would be followed by one of the data write operations. And rather than adding to the write position, if I simply provided the correct address for the operation, then I could save some cycles in the address computation. So I just had 2 versions of each of these operations, which added an address which I just needed to read in and set the current output pointer to. And this worked really well, but I did start to expand the process out a little bit further. So I've got space here for 256 tokens, so I can add a few more to optimize common cases. The first I added was byte operations. Now with a single byte change in an area, there's no real difference between the run length or the raw data types, and this saves us both the byte for the length, but it also reduces the decode cost quite dramatically for those 1 byte changes. If we jump across to the code here, you can see I implemented those operations, but I also added some additional common cases with exact counts of the amount of data being copied, because those unrolled loops make for much faster handling of those common cases. And how did that work out for us? Well, only 23% of the frames complete in the vertical blanking interval. So I need to do something about that. So firstly, I added code that calculates the number of cycles for the decompression as I'm building it. And then I cut the compression and therefore the decompression of a frame short under one of several circumstances. The size of the data gets too big, the cycle count approaches the end of the vertical blanking interval, and I also imposed a cap of 256 tokens just so I could store the token count in a byte, and I wasn't expecting that to be a significant restriction. It wasn't. Now earlier on I did point out that the source video was 30 frames per second and VGA is 60 frames per second. So we have 2 VGA frames per source video frame. So if we pick up where we left off in the next frame, then 65% of frames complete by the end of that second frame. And that's a lot better. But fast changing frames are going to show some artifacts. Now one particular case I wasn't happy with the results of, so I wrote some special handling code. At several points in the video it dramatically inverts the black and white. And if we look at the frame delta here, absolutely everything has changed. So what I did was I wrote some extra code that could spot the frames where this inversion happened. Now I could have tried to introduce, say, a palette inversion, which would have made it trivial time, but it would have complicated some of the encoding and decoding because I'd have to track when the data was different. The simplest thing I could actually inject into the pre-existing data pipeline was to swap the indexes of the solid black and solid white tile. So if we take this starting point and see what happens when I do that, it's obviously not correct, but then when we look at the interframe delta, it's far more reasonable. We've got big areas of solid black and white that are unchanging, and then we've just got the boundary bits where we've got some copy and some run length data to deal with. And then the conversion to the final frame is much simpler, and we can let the standard compression decompression code take care of that. So the big question is, could we optimize more and further improve the fluidity of the output? Well, of course we could. I've got a lot of ideas for how I could improve it, and I've even come up with several more ideas just making this video. You can almost always optimize code a bit further when you've got a sizable complex system, but it is worth noting that process is subject to diminishing returns. I could maybe get it 50% faster by putting many times more effort into it than I've already done, and this whole demo has already taken me a lot longer than I had originally hoped it would. So sooner or later I had to stop and say, well, this is good enough. I'm actually very pleased with the results I've got, even though there are a number of imperfections in it. Now my ideas for improving this, I've got several. I could make more special cases. One thought is I could use the hardware scrolling to help deal with the fast left to right motions, which tend to cause large deltas. There's a number of small operations I can do to optimize the code itself, but would give us scope for slightly more changes within the vertical blanking interval. I also think if I held off streaming additional data in particularly troublesome frames, I could write some special operations which could fit a few extra bits of update into the horizontal blanking intervals. And whilst they're not very big, there is 480 of them in a frame if I'm not having to stream any data in. The last thing to talk about is the audio, and I knew from the get-go it was never going to be the best part of the demo. I don't have raw wave output. When designing the audio circuit, I wanted to go very basic. I started off modelling things after the single tone output that the early IBM PCs had, and we expanded that, created multiple channels with a little bit of volume control, but fundamentally the circuit is very simple in its capabilities, even though we've done some interesting things with it. Could I add wave output? I mean, of course I could. But it didn't really seem in keeping with porting the demo to add custom hardware functionality to support stuff. Otherwise I'd end up tearing down the entire system just building dedicated bad Apple playing hardware. And this is really about trying to see how good a representation of the demo I can create using the systems that we built. So the option is to use the synthesizer. And the music demos I've done before have been converting basic MIDI tracks. So I spent quite a bit of time looking around, and the most appropriate MIDI track I found was this one. This was made by a YouTube creator called Ronald McDonald, and I think he did a pretty good job of it. Now the MIDI tracks I've done before were just done with basic electric piano type effects. And to pull off a more complicated MIDI track like this, I needed different instrument types. So I spent quite a lot of time expanding my basic MIDI conversion system. Now I did limit myself to this 60 Hz change. That's because I wanted my update to line up with everything else I was doing that was going to be heavily synced to the VGA update rate. Now I mentioned that I decompressed the audio first after detecting the start of the vertical blanking interval. And while that sounds counterproductive on the video side of things, it was quite important to do on the audio. The decompression of video could take a very varied amount of time. So if I did it after the animation decompression, then the amount of time between the audio updates would actually vary quite a bit between frames. By putting it at the start of that interval, we get what Martin from Wintergarten would refer to as type music. And I felt while the audio hardware is very simple and our reproduction was never going to be particularly great, it was important to get the things right that we could. So I had to set about creating different musical instruments, and I did that by creating different variations of the ADSR parameters. I also added controls for volume modulation and for frequency modulation. And that actually just became a process of trial and error, just listening to different instruments and trying to create an interesting set of values for those controls, which made them distinctive and interesting, if not particularly authentic. I'm not an expert at music. I did the best I could. And that took care of the main instruments. But the track also had percussion, and that was tougher. So the first thing I did was get some sound samples of the different percussive effects, and I started to look at the waveforms. I did frequency analysis on those waveforms, and then I picked the dominant frequency and volume for each of those in a 60th of a second window. My thought was to use one channel and play that back whenever the percussive effect happened. Let's take a look at the results. So this is the waveform for a hi-hat, and you can see it's actually quite complex. The reconstructed version I created, very simple. You can see the 60th of a second changes. And whilst the coarse profile of the sound does approximate it, it's very rough. Here's a whistle. And again, we can see it's very rough, but it does have a kind of reminiscent effect to it. If we zoom right in, we can see there's some amplitude modulation that the 60th of a second intervals we're dealing with is just nowhere near enough to reproduce. Maybe a couple of hundred hertz and we'd see a very different response here. So here's a tom-tom. There's a lot of subtlety to that music, but obviously it's very punchy at the start as well. So the reconstruction has the same shape, but the kind of digital coarseness that gets pulled out of these is just a byproduct of how simple the synthesizer we built really is compared to the subtleties of real music. And one of the most difficult ones is that punchy bass line that the music starts with. I couldn't find any good free samples that sounded right, so I actually clipped one of those beats from the original video and attempted to process that. And the results are what you've already heard in the demo. None of these are going to impress anyone, but when we put them all together with the music, we definitely produce a very recognisable form of the Bad Apple music. So overall, we met our objectives there. And the overall result of the demo, I'm extremely pleased with. Well, I do hope you found that interesting. If you've got any more questions, always drop them down in the comments. I try to answer everything that I see there. It's also worth joining the channel's Discord server. There's over 1,000 people on there now, and there's always some interesting conversation. As always, thanks to everyone who supports me. I really do appreciate it, and I'll see you again soon. Goodbye.